Excellent. Okay, just give me 1 second and let me let everyone else in. I'll just give that another minute because we've got some people that are still joining. Looks like we're pretty good. Excellent. Okay, let's get started. So greetings, everyone. Welcome to today's Terrestrial webinar. My name is Carolyn Swain. I'm the Director of Marketing for Vertical Aspect, and I'm thrilled to be your host for this session. Thank you all for taking the time to join us today. We have an excellent presentation lined up that I know you'll find both informative and valuable. So before we dive in, let me cover a few quick housekeeping items. This webinar is being recorded and will be available for viewing afterwards. You'll receive a link via email. Additionally, all attendees are currently muted. Please use the Q&A function to submit your questions throughout the presentation. We'll address as many as we can during the Q&A segment at the end. Oh, give me 1 second. We've got some folks coming in still. Fantastic. So let's get started. Let me introduce our presenters. We are fortunate to have Arttu Sonanen and Christian Stallings with us today. I know you're eager to get started, so without further delay, I'm going to turn things over to Arttu to begin our presentation with machine learning classification. Arttu, the floor is now yours.
Okay, thank you. So Terrascan has a machine learning capability for classifying above ground features. We do need to have ground classified, and typically we would classify into low, medium, and high vegetation. And I would handle some objects before moving to machine learning. I would definitely want to find wires. Especially if there's power line wires with a good number of hits, I get a good result with find wires automatically. There's a recent tool, classify linear features, which I would also use to find fences. And then when I have those linear objects classified, then I can move to machine learning. I may also decide to handle some other objects, such as buildings, outside the machine learning. The machine learning is always based on training data. So you need to have some blocks of data carefully classified so that we can provide examples to the machine learning model. And you build the machine learning model using a tool called train model. And then you can, when you have a trained model, you can classify rest of the blocks in the project using that model. So train model is the main tool when building a machine learning model. It works on parameters computed from groups. You can select a number of parameters from quite a big extensive set that Terrascan can compute. And while you are adding parameters to your model, you will get information in the dialog showing how good the parameters really are for separating objects. And the parameters will also help you improve the classification of your training data. And I'll show that pretty soon. Parameters fall into 3 categories: geometric, radiometric. Radiometric means that it comes from intensity, or color. And there is computational parameters, which are a little bit more complex. Here I have training data, which I believe that I have carefully classified. I have handled building roof class, the red class, in all of the blocks separately, using footprint polygons as an aid. And I do have building footprints visible. Rest of the classes visible are things that I want to classify using machine learning. I keep also building roof visible because that helps me understand one of the classes, which is building structure, the white class. And the classes I have visible are the ones that I try to classify using machine learning. I have a vegetation class. That's vegetation which is less than 4 meters in height. I have a building structure class, which is anything right next to a building, or above a building, which you can think of belonging to a building. I have a tree class. That's vegetation which is 4 meters or more in height. I have a car class. I have a pole class. Poles in this airborne dataset show up like this. They don't have so many hits on the vertical pole itself. I often have just some points which are floating in the air in the point cloud. And I have a structure class, and that's a very generic class. It's any man-made objects for which I don't have a dedicated class for. And I have a class called machinery, because in this dataset there's quite a lot of machines on this yard. Diggers, tractors, and other machinery items. And I believe that I have done a pretty good job in classifying training data. So I can go to train model, and I would select all the classes that I want my machine learning model to classify. I don't necessarily want to use every one of the examples. I only have 28 machinery groups, whereas I have almost 3,500 vegetation groups. So I limit the number of groups to use to 500 per class. And I reserve 25% of the groups for validation. So the software uses 75% to train a model, and then it can use 25% to test if the model classifies the validation groups the same way as I have classified. And I can then start adding parameters. The first parameter I'm going to add here is maximum distance. Comes from the geometric, the simple parameters. When I click on a parameter here, I see what is the smallest value that a group gets and what is the biggest value that a group gets for each class. And I see a graph showing the distribution of the values for each one of the classes. I don't like the fact that I have some vegetation group is 20.76 meters high. My rule is that anything which is more than 4 meters in height, that should be a tree. So when I start adding parameters, I do discover flaws in my classification. When I have only vegetation selected, then this here, which is a list of groups, shows me only the vegetation groups. And I can go to the end of the list and find the highest value group. And I can see that it's not vegetation, it should be tree. So I'm going to classify that one as a tree. And I remove it from the list from the set of groups that train model currently uses. I have another one which goes to the height of 6.6. And this one is a really special case. It's fallen tree trunks. So I don't want to have it as a tree. It's not a normal tree. So it's not good as training data. And I don't really want to have it as vegetation either. It's such a special case. So this one I'm going to classify to high vegetation and remove it. And then it's outside my machine learning examples that I'm going to use to build a model. I do want to add additional parameters. Maybe I add width, another simple geometric parameter. And I can see that it has some value. All the poles have a smaller width than any of the cars or any of the machinery groups. So there is value in width. It gives me some separation of classes from each other. And I would add perhaps something from the radiometric. Vegetation index I can use whenever I have color information on the points. I do have RGB color, and usually vegetation index is good in separating vegetation and non-vegetation. Here, the images were taken at a time when the vegetation is not so green. It's somewhat brown. Early in the spring, when the deciduous trees don't yet have full leaves. So on this dataset, vegetation index is not as good as I would hope. But I would still maybe want to use it to find outliers. So I would expect vegetation to be more green. I would expect vegetation to have bigger values, and I may want to check those places in the list where I have the smallest vegetation index values. And I can see that, okay, this here is not vegetation, it is structure. And in this way, I would continue using the parameters to find outliers and improve my classification of the training data. In the computational, I have more complex parameters. Transparent ratio is quite good in separating trees from everything else. Trees are typically higher values. I have a building structure class, and the rule is that building structure is something close to building roofs. So I need a close by 2D ratio parameter. And then my building structures should typically have a higher value, not zeros. So the zeros are a problem. So I have something classified into building structure. Let's find the first one which has a 0. Which is not really that close to a building. And I would rather have that classified as structure. But I would keep on adding some parameters and filtering or improving the classification as I go on. Maybe I add one more. I add rectangularity from the geometric. And at some point, I can run training. I now get a 94% success rate. So that is in my report. So now I have a model that can classify groups. And I can see that for the vegetation groups, I get a 96% success rate based on the validation examples. My weakest is structure, where I have a 66.7% success rate. But when I have my first model built, then I can look at only those groups where the model gives a different result than what I have provided. And then these are the ones that are likely to be badly classified in my training data, or it is cases where the model does not give the same result. But I would go through these ones to further improve the classification of my training data. When I've done editing of the training data, at some point I would end up with a set where I can't really see flaws in the classification. And now I open a version of the dataset where I have gone through that process that I feel like this here starts to be clean. I say rebuild groups. So now train model recollects the groups from the active point cloud. And now I would show that I would use add best next. And this one adds optimal parameters that the software chooses. So you don't need to know the meaning of each one of the parameters. You can make the software choose the parameters that work the best. So the software tries to add each one of the parameters one at a time and sees if that improves the model. And it adds the parameter which gives the best improvement to the overall success rate based on the validation examples. And after adding one, it repeats the process. It tests each one of the remaining parameters if adding that one improves the model and by how much based on the success rate. And so this process is somewhat heavy computation. It does take a little bit of time. When I have a final model to be used, then I would save the model, and I can use that model in classify groups using trained model, which I can run as a macro to classify rest of the blocks in my project. My computer is still busy doing the add best, so I will mention while we wait that there is a YouTube video on machine learning classification. You can find it if you Google YouTube Terrascan machine learning classification, and it shows the machine learning steps and it gives you more time, shows more details than I'm showing in the webinar. So I recommend viewing that one to get a good understanding of the machine learning workflow. And I expect that pretty soon the add best is done. So it adds a handful of parameters to the model. And then I can run the training, look at what is the success rate that I get. And after getting my final model, my final set of parameters. So now after rectangularity, the at best decided to add area, average jet ratio, minimum distance, planar ratio, group verticality, and so on. And I can now run training. And now I have a 96.6% success rate. My weakest one is structure with a 69% success rate. Structure is difficult as I have so many different kinds of objects in there. There's everything starting from trampolines on people's yards in that class. But I'm now in a position to save the model, or I can do the following, that I say, let's not reserve anything for validation, that now I want to run the training with all the groups. And this gives me more training data. Then I don't get any information on the success rate, but perhaps my model is now a little better as it's using every possible example. And I would save this as a TDF file. And then I have the ability to classify other groups, other blocks, using that trained model. I'll now open a project which references those blocks which I have not used as training data. And in this one, things are in medium and high vegetation class, but grouping has been run. And then the software can use grouping to classify things from the medium and high vegetation class into the 7 result classes that I have chosen. And this one is simply classify groups using trained model and using the PDF file which I have just created, and starts from classes 4 and 5. And then I have the result. In this place, the cars look good. These are classified as structure. That looks good. There might be a car in here, so the structure and car can be close. And of course, there's the white stuff which is right next to a building or above a building. Trees have been classified, vegetation. The success rate I got from the report, 96 point something. I do not believe that the final classification is 96%. The training data was edited, and when I'm doing the editing, I also modify grouping so that I would have clean examples. And on the rest of the blocks, I haven't done any editing of the grouping. So the grouping has some flaws in it. Sometimes multiple objects end up in one group. So the success rate is always, the actual final success rate is always below what the report gives us. But that's the machine learning workflow, all the main steps quickly shown. Thank you, and I'll pass things to Christian for the next 2 topics that he will show. Thank you.
Thank you, R2. The next new features that we're going to demonstrate is the change detection between 2 point clouds using Terrascan. By comparing 2 point clouds collected at different times, Terrasolid users can identify areas of change in a given location This can be useful for counties or municipalities interested in identifying objects that have either been removed, such as trees, or conversely, identifying objects that have been added, like buildings, which can be useful for planning and zoning departments who want to track change within their jurisdiction. So the steps that we're going to go through today in this workflow, we're going to set up the extra attributes, which is an option that was added in Terrascan that allows us to store our custom attributes. This isn't entirely necessary for this workflow, as we can store it in the regular distance attribute, but by adding an additional distance attribute specific for change, we can store our change values in there. We're going to show how to read reference points for individual files into Terrascan and how to visualize both our active and our reference point clouds. Next, we'll go through the compute distance between active and reference point clouds so that we can visualize those. And then we're going to show how to do this same workflow instead of just on individual tiles, on entire projects, and run our change detection on entire projects. So we're going to start by bringing in our most recent data set. We have this data set here from 2024 that we're going to bring into Terrascan. And we have our classified data. The next thing we're going to do is we're going to go ahead and set up our extra attribute that we discussed. So if we go to the Terrascan settings and we go to the extra attributes, we have the ability to add different attributes. You have either number, lists, class, distances, or reliability. In our case, we've created an attribute called change, which is a distance value. It's a 32-bit integer. We want to save any custom attributes that we created. By default, those extra attributes will be saved into the root directory for Terrascan. Next, we want to go ahead and read in our reference file. So we have an option here to read reference points, which allows us to bring in an additional LAS file or point cloud file. We're going to bring in our point cloud file from 2021. Now that we have both of our point clouds in, we can go and look at our data and draw some profile lines. And we have the ability to visualize in our view 2 our active versus our reference files. You can see here that our active files are in white and our reference files are in red. And you can see right here, we have an example of a tree that was here in 2021 that is no longer there in the 2024 file, but many other objects are still coincident with each other. Next, we're going to go ahead and compute the distance between these two files. So we're going to go to our tools and compute distance. We have the ability to compute against different classes. We're going to go ahead and do every class. And within the different distance measurements that we can do, we're going to do the active versus the reference. We created that new attribute for our distance called change. So we're going to make sure we select that as our attribute to store our change value. Right, we've calculated the distance between our different points. Now we can go back to our view 1 and we can change our view so that we can look at the distance that we have calculated. We have this dropdown now that has that change attribute that we can show our distance change in, and we're going to go set up our color scheme. And we have the ability to show either the active points or the reference points or all the points. So we're going to start with the reference points. And this allows us to see the change in our reference points of areas where we had objects in 2021 that we no longer have in 2024. And you can see this area right here. We have some trees that were there in 2021 that are no longer there in the 2024 data set. So in our reference points, we can see these different objects. Conversely, if we want to look at items that have been added since then, we can select our active points, and we can go visualize buildings that have been added or other objects that have been added since the 2021 data was collected. So here's an example of a building that was added that was not there before. And from here, we have the ability, we can look at individual classes, and we could export different derivatives of the change detection. We can subdivide the point cloud into various classifications, further segmenting it. We can create different rasterized products showing the change, or we can vectorize these objects to bring into a GIS environment. Next, we're going to show how to do the similar workflow except on a project. So we're going to open up a different project. We're going to select our defined project, and we're going to open up our project for this data set for Helsinki from 2017. Within our projects, we have the ability to set up reference projects. So this allows us to reference a similar project to the project that we're working in. In this example, we have this data set from 2021 that we're going to reference for this project. Within our macro tools, we have the ability to run the compute distance with the same settings that we ran before. So we're running the compute distance, active versus reference, and similar to before, we're storing those attributes in the new attribute we created for change. With that, we have the ability to run a macro, and we want to make sure that we have the load reference points selected when running the change detection. We can also distributively process our data set. In this example for the webinar, we just have 4 tiles. They'll go quickly, and we can go ahead and run our change between the 2 data sets. And this will compute that distance and store the change attribute within our point cloud. All right, so we ran the 2017 data set to the 2021. This allows us to see things that were removed, but if we want to also see things that were added similar to what we were looking at before, we need to go ahead and run the same steps on our newer data set. So we're going to select the 2021 data set. We're going to make sure that our project is set up similarly to have our reference project. In this case, we have the 2017 data set reference to our 2021 data set. We'll go ahead and run our macro again, and again, ensuring that we have the load reference points selected for our macro. Right. With our most recent data set open, we can go and look at some of the blocks that we have done our distance classification on. When we load the blocks, we want to make sure that our load reference points is selected for the blocks that we're going to view. All right, in this example right here, we are looking at our active points. And so we can see, again, areas where items have been added. So if we look at this example right here, we can see the change in these areas. And if we go and investigate, we can see where some trees were removed and a new building structure was created in these areas. And similar to looking at the individual tiles, we could then export different derivatives from this if we wanted to populate a GIS with different information about buildings that have been added or trees that have been removed. All right, for our next workflow, we'll show how to remove window reflections from terrestrial LiDAR point clouds. One of the challenges with terrestrial and mobile data is the reflections that windows can create, causing ghosting or objects with incorrect locations within our point clouds. In this example, you can see from the images here, we have an example of some laser pulses traveling from the terrestrial setup, which you can see with the red vector, and it reflects off of a window to the tree behind the scanner, which is shown in the yellow vector. But unfortunately, the scanner cannot determine this, and it misinterprets this position of the trees and other objects being along that same vector line, putting them in the wrong place, causing ghosting of those objects. So we're going to do a couple different processing steps to try to correct these ghosting objects within our data set. So we have several different terrestrial scans that we're going to go through. We have 15 different scans. We're going to use the deduce scanner position tool within the trajectory toolbar that will allow us to determine the location of each of those scans. We're going to remove some of our long ranges from our data set, cut the overlap by range to further thin our data, and then finally we're going to thin that data down to a 1 centimeter sampling. Once we have that, we'll vectorize the wall polygons, and we will use the inspect element tools to check those wall polygons and do edits to those polygons to then finally use those as planes to determine any window reflections that pass to those planes that we want to change the classification on. So we want to go ahead and read in our files. Here you can see we have 15 different terrestrial scan setups. They are LAZ files, so they are compressed, and will take a little bit of time to decompress. We're going to set this up as stationary LiDAR for these scans, and we're going to go ahead and import those into our data set. So this will take just a minute to bring those 15 scans into our data set. Here we are. We have all of our 15 scans in here, and we can go look at some of the attributes for these scans. So if we go and investigate it based on line, you can see that when we brought them in, we were able to sort them as individual scans. You can see the circles representing the different terrestrial scan setup locations. We can see some outlines of some buildings where we have what look like trees that are inside the buildings. We also have these areas here where we have tree objects outside the buildings, but they don't appear to be in the right locations. These are some of the potential window reflections that we want to remove. If we go look at our echoes, we can see that we have multiple returns per pulse. And because we have this information, this allows us to create vectors along those pulses for each of the returns to determine the scan position that the sensor, or excuse me, the terrestrial station was set up at. So we want to go to our Manage Trajectories tool. And under our Manage Trajectories tool, we have the ability to deduce the scanner position. And we're going to use the multiple echo vectors from those multiple returns from each pulse to determine those positions. All right, so we now have 15 different locations from the 15 different scans. I'm going to change this back to line so we can look at this. And so if we select these and select show location, we can see the estimated location for each of these, and we can toggle through these and make sure that the location appears correct for the scan stations. And it looks like we were able to determine the location of all these different scan positions. We can go ahead and close our trajectory tools. Next, we want to thin our data. We're going to go ahead and first classify everything to class 1. And then we're going to classify by range. And we're going to remove some of our long points that we don't want to use in our data set. So now we've removed some of the long ranges that are beyond 100 meters. And we can go ahead and delete those from our data set. And so right now we have 145 million points that we're starting with. And we're going to continue to remove some of these points from our data set. The next tool we're going to use to thin down our data set, we're going to cut overlap for our data set. Before I do that, I'm going to draw a profile and show you some examples of some of these areas. Where we have information from multiple different scans. So using the cut overlap tool, we will go ahead and cut by range and classify those to the overlap class. All right. So you can see in this example here where we have removed some of those overlap points, and we still have quite a bit of hits on all of our objects that we want to classify. We can go ahead and remove those points as well from our data set. So we start with 145 million points. We're down to 132. And we want to do one last bit of classification or noise removal. We're going to get rid of, we're going to thin our points to a, down to a spacing of 1 centimeter for all of our points. We're just going to go ahead and delete those. And the method we're going to use is by density and keep our central points. All right. So we started with 145 million points. We're down to 52 million points, but still have quite a bit of information and detail in our data sets. Go back to the line. And so we can still see some of these objects that we want to clean up in that data. A great tool that we have within Terrascan is the Inspect Points tools. We can look at various different attributes that we can visually display. For our use case, we really just want to look at the vector, the pulse vector of those returns to those different points. By doing so, we can see the path of each of these individual points. So by looking at some of these trees objects that we see within the buildings, we can see that the actual scan station that they're coming from is on the other side of the building. And if we look, we can see these same objects mirrored on the other side of those scan stations. So for example, we have these points in this building representing the trees coming from this red line, which are a reflection of the trees that are actually behind that scan station that are misrepresented inside of the building. So we want to temporarily classify some of our points by range. Again, we're just going to temporarily move some of our points to a different class based on a distance of 50 meters. And this is going to allow us to reduce down some of the noise in the data while we build our vectorize our wall polygons. So we've just temporarily moved those to a different class. Using the Vectorized Wall Polygons tool now, we can go ahead and start creating polygons for the walls within our dataset. We're going to use the default class that we're using, and we're using a fairly loose tolerance of 25 centimeters and a minimum area of 4 square meters to vectorize these walls. And it's going to go ahead and estimate the planar features that it thinks are walls based on this data set. And as you can see, we have all these different wall features that were created. If we go and inspect these, we can see that some of these aren't walls, some of these are the sides of buildings, some of them are the sides of cars or other objects. So for example, we have the side of what looks like a trash bin. And then in areas over here, for example, we have some fences that we want to remove from our data sets. So we're going to go ahead and manually remove some of these different objects from our data sets before we start the Inspect Elements tools. The ones that we know are actually some of the building walls. We're not looking to perfectly represent the walls for this data set for modeling purposes. We're really looking to create the planes in areas where we know that points should not pass. Either there's a wall where it would hit or a window that it reflected off of, which is more important. So we can go ahead and do some initial cleanup in areas that we know are incorrect from these polygons that were generated. Oops. Let me do that. Now that we have our polygons thinned down, we can go ahead and select all of the features, and we can use the Inspect Elements tool to systematically go through all the different features that we have generated. We can set our views in different ways. In this example, we're going to have our top view, our plan view to 1, and then we're going to use view 2, which we have over here, to set to our plane view with a depth of 25 centimeters. This will create a list of all the different vector features that we can go through systematically, and then we have the ability to create different action buttons for that list. In this example right here, we've created an action button to accept the polygons that we want to create as they've been generated. When we accept an element, it's going to modify that element by removing it from our list. It's going to change it to a different level. In this example, we're using level 14. And we're going to change the color so that we can keep track of the polygons that we've gone through already versus the ones that we still have to review. If we don't like one of the polygons that we've created, the delete button that we created in the action list will just delete the element and remove it from our list. So we're going to go ahead and run this, and it opens up the Inspect Elements tool. We can select some of our objects, and we can make decisions on whether or not we want to keep that object as it is or remove it. So in this example, we have a wall that looks like it needs edited. So we can go and we can digitize a new feature for here. And we can remove or delete the one that was estimated. When we're going through this process, we're again primarily interested in planes that have windows in them where we have the reflections. That's where we're going to have the window reflection issues. We want to make sure that the polygons that we digitize, again, do not have to be perfect, but we want them inside of our shapes, our planar features, so that any points that truly do pass beyond that plane will be kept. So in this example, we have some windows down here. We want to make sure that the polygons that we have cover those areas and remove the old one. And we can systematically go through all of our different polygons, removing them from our list and moving them to our new level, which is level 14 in this example. And you can see as we're going through these, they are changing color and being removed from our list. We're going to go ahead and fast forward for webinar purposes. We've actually digitized all these walls already. Go ahead and remove the ones that we put on layer 1 and 14. And we've already gone through the process of digitizing all those different features. Once we have those planes generated, we can select those different features. And we can go to Classify, Noise, and we can select the new Window Reflections tool. We're going to start from class 1, and we're going to classify into our low points, and we're using a fairly loose tolerance of 0.5 meter. And as you can see, we've classified a lot of these points that we were observing earlier in the data set. So if we go and look, for example, over here, we have what appears to be a tree outside of the building. But again, if we go back to our inspect elements and we look at those vectors, pulse vectors for that particular object, we see that it's not actually inside of, or excuse me, out on that side of the building. It comes from a scan station that's on the other side of the building.
So Christian, I think you have some points in
I did miss
building
a step.
roof glass. So if you run that,
you're right.
Also on building roof, the window reflection classification.
We did skip a step. Let's do that again. Thank you, R2. We forgot to, I apologize, forgot to classify the points that we temporarily moved to a different class back. So let's go ahead and select those buildings again. And let's run our window reflections again. There we go. That's much better. Thank you, R2. So if we look at those areas, we can see we've fully accounted for all those points that we had temporarily moved to a different class. We have all of our trees that are misrepresented in this between these two buildings here as well. And if we turn those off, we can see that these areas now might look much cleaner, and we've removed those incorrect locations of those points from our data set. We can then go ahead and delete those points. And we can save our data set, and we can continue on with any further classification or extraction that we want to do from our point cloud. So that concludes the demonstration for the window reflections. I'm going to go ahead and hand it back to R2, and he's going to demonstrate the Gaussian splat workflow inside of TerraScan.
Okay. Thank you. So the last final topic that we cover in the webinar. So we've only chosen a few key topics among the new features, so that the webinar isn't so long. The final one is Gaussian Splats. So there is development done at Terresolid for Gaussian Splats. Gaussian Splats, it's a technique for representing real-life scenes in 3D. So it's a visualization method. Gaussian Splats give us a photorealistic visualization model where the viewer can move. So it is full 3D. One description of Gaussian Splats is that they are semi-transparent ellipsoidal blobs of color. The source for Gaussian Splats is always images. You must have images to generate Gaussian Splats. But for TerraScan, what is really the key thing is that the Gaussian Splats, it is a point cloud. It is X, Y, Z points with some properties like size, rotation, color, opacity. TerraScan cannot generate Gaussian Splats, but we can read Gaussian Splats in. And the main file format for those is PLY. So there is something called extra attributes now in TerraScan. TerraScan can read point attributes which it doesn't have built-in logic to make use of. But it recognizes that there is some values associated with the points, and there is a name and there is a data type. And we can read all of those into Terrascan. We can manipulate the point cloud, such as classify, modify coordinates, delete some points, and then we can save the resulting point cloud into a PLY file, or we can save to an LAS or an LAZ or a fast binary. All of those 4 file formats support extra attributes and thereby support Gaussian splats. Terrascan displays splats as points. It doesn't have full Gaussian splat display engine in it. But we do have 2 applications at Terrasolid which do have full Gaussian splat rendering capability. One is Terrastereo. So it provides full Gaussian splat rendering on MicroStation, on Spatix, or as a standalone. It can also act as a display engine extension for point cloud with splat information loaded into Terrascan, which gives you the ability that you can read splats into Terrascan, classify some splats, delete, move the data to the right location in the world, and you can use Terrastereo to visualize the point cloud as full Gaussian splats. Gaussian splat display is heavy computation. It always requires an NVIDIA graphics card. Something like 8 gigabytes of video RAM is recommended on the NVIDIA card. Then we have another application called TerraSplat, which hasn't been released yet, but it's going to be released soon, which has the same capability. It can act as a display engine extension for Terrascan. And it is priced quite aggressively. Annual subscription, 350 euros. And it can do the same thing as Terrastereo. It comes from the same source code, but it is only some of the Terrastereo functionality. So it can display Gaussian splats on MicroStation or on Spatix. And you can run TerraSplat without Terrascan. And it also requires an NVIDIA graphics card. So Terrascan itself doesn't require an NVIDIA graphics card, but TerraSplat does require an NVIDIA graphics card. I'm going to read in Gaussian splats, which DJI Terra software has generated. So if you have drone images, you can create a set of Gaussian splats using DJI Terra software. Another software which we have used Gaussian splats from is iTwin Capture Modeler from Bentley. And what is nice about these 2 packages is that they can give us a point cloud of Gaussian splats which have real coordinates, projection system coordinates. DJI Terra doesn't write the coordinate system into the PLY files. It's in a file called metadata XML. And I'm going to select this file so that the software finds the coordinate system information. And Terrascan will then look into subfolders and the best level of detail where there is PLY file. So when I select the XML file, Terrascan gets the location in the world, and it finds 4 PLY files that it actually reads in addition to the 1 XML file. So it displays here that it's reading in a PLY file. It has found projection information from the XML file, longitude, latitude, elevation, acting as a center point for the local coordinate system in which the PLY files are stored. And I will say that this here is airborne photo. And I specify a projection system in which I want the data to be in. So the Gaussian splats have X, Y, Z, and they may also have normal vector, and they have color, opacity, size as scale parameters, rotation, and then there's a DJI Terra specific filter 3D. All of these are extra attributes for Terrascan. So some of those Terrascan has no dedicated software code to handle. They're just extra attributes. And now I have a point cloud which has extra attributes in it. And it is the Gaussian splat information. I can look at this with elevation coloring. I can give you a cross section so that you will get some understanding of what does the Gaussian splat point cloud look like. And when we look at a cross section of a building, I can see that it is quite noisy. So typically Gaussian splats are much noisier than a LiDAR point cloud and much noisier than a photogrammetric point cloud. And in addition to having points on the building walls and the building roof, we also have some splats or points inside the building. And this makes the Gaussian splats more difficult to process, more difficult to decide that these are the points which represent one object, such as a car or a tree, because there is so much noise in the Gaussian splats. Terrascan can only display the Gaussian splats with the same settings as we have for LiDAR points. So I can display the Gaussian splats with color. And where we have water, so this here is an island, and we have sea water surrounding it. And in the water, we really have 2 images of the water surface. I may do manipulation, such as delete unnecessary points which are clearly from the seawater and are very noisy. And I can view my point cloud the same way as Terrascan can view any point cloud. But this is as good as I can make it look like with Terrascan alone. But if I also have TerraSplat or TerraStereo, then I say update loaded, and then it will load the points or splats in Terrascan, build its own indexing, its own tables, which are stored during the rendering, are stored on the graphics card to some extent. And then I have in my display mode, I have the ability to change color by to be splat. when the color pie is splat, then Terrascan is not going to draw the points into a view window. Instead, Terrasplat is now doing the rendering using the NVIDIA graphics card on my computer. And now things are rendered using the full Gaussian splat rendering. Capability. And everything looks much more photorealistic than if displayed using just one RGB color per point. And so this gives you the ability to do things with Gaussian splat point clouds. You can visualize the Gaussian splat point clouds using full Gaussian splat rendering. And whatever you do, you can save the work as an new PLY file or an LAZ file if you want compression, or an LAS file or a fast binary file. There is also a merge splats tool in Terrascan. So I said that the Gaussian splats are more difficult to classify than a LiDAR point cloud. So the Gaussian splats are for visualization, but not so much for survey or measurement. We really want the LiDAR point cloud and the Gaussian splats to come together. We'd really like to have LiDAR point clouds which are Gaussian splats at the same time. Merge splats tool gets us a little bit closer to that goal. If you have a LiDAR point cloud and Gaussian splats from the same site, then we can merge the Gaussian splat parameters into the LiDAR point cloud, so that if we classify the LiDAR point cloud, we can switch off tree class from a view, or we can delete an unwanted object, or even make copies of some objects. So I'm now going to use the same splats, but this time I first read in a LiDAR point cloud for the same site. The LiDAR point cloud was collected using DJI L1. And I have 22.9 million LiDAR points. And the LiDAR points, they do have color, but the color is computed from the camera, which was on the L1 system. I also have Gaussian splats for the same site. For the Gaussian splats, and a second flight was used. So both the L1 flight with vertical camera images and a second flight with an oblique looking P1 camera. Both image sets were used to create the Gaussian splats that I already showed you. But with merge splats, I would select the same XML file so that I get the Gaussian splats to the right location in the world. That's the only way they're going to match the LiDAR point cloud. And the Gaussian splats are ellipsoidal, so I do want to apply a geoid correction to go to orthometric. And I have settings 0.5 meter maximum distance, and non-linked splats add as points into class 21. Maximum distance of 0.5 meter means that LiDAR points copy splat parameters from the closest Gaussian splat within a distance of 0.5 meter. Not every Gaussian splat has its parameters transferred to a LiDAR point cloud. So we also add some free Gaussian splats, non-linked Gaussian splats. So 14.2 million of the LiDAR points received Gaussian splat parameters. And then there was almost 10 million splats which were not transferred to any LiDAR point. I now have the same that the Gaussian splats had a lot of points in the C. I'm going to delete those. Those are not needed. And if we go and look at a cross-section from the building, the same place we looked at earlier, that's my LiDAR point cloud. And it is much cleaner, a thinner line on the ground, on the building roof, on the walls. And many of these points now have Gaussian splat parameters. But to get the full Gaussian splat display quality, the software needed to also add some of the Gaussian splats as free splats. And those are in a dedicated class 21. But this gives me the ability that I can now classify the LiDAR point cloud and copy the class to the Gaussian splats from the closest LiDAR point cloud, the same way as we handle inactive points in the wizard drone processing. Right now, I'm displaying the point cloud using TerraScan alone. It now has both LiDAR points and it has Gaussian splats, all displayed simply as points. And I can do the same that I run TerraStereo or TerraSplat. I do the update loaded. And then I have the ability to, if I want, in one of the view windows or some of the view windows to color by splat. With DJI L3, DJI has Gaussian splat generation as one of the LiDAR end products. So DJI is also working on bringing the LiDAR point cloud and Gaussian splats together. And I do believe that in many of the cases in the future, people will use Gaussian splats as a visualization method for LiDAR point clouds. Thank you.
Excellent. Thank you so much, Artu and Christian. We really appreciate your time. Hey, let's take a few minutes to address some of the questions that have come in. That was a lot of information to cover, so there must be quite a few.
If anyone has any questions, there's the Q&A button. Please go ahead and paste your questions in there and we'll answer those.
Yeah, I can see one question, which is, I have received a few macros that was emailed to me. I think they are in meters. How can I adjust them to US survey feet without multiplying them by 3.28? And there isn't a capability in Terrascan to transform a macro from one unit to another. But I do take this as a development request, so I will add that to my list of things to develop. So in some future version, there will be a capability to convert macros from one unit to another. Thank you for the excellent question.
All right. Do we have any other questions?
There's a couple other in there.
Oh. Here's one, R2. Are trained models compatible with feet and meter coordinates, or does data need to be scaled or retrained? It's an excellent question.
There is a few settings in the machine learning parameters which are in whatever is your working unit. So you may remember that I added close by 2D ratio as one of the parameters, and it had a setting for finding how many of the points have building roof within 1 meter. So I'd say that maybe 5% of the parameters have a setting which is in your whatever is in your current working units. So this means that you have to do some modification to those parameters if you have trained a model using meters and you want to run it with a data set in feet. But it should not be a long exercise that if you have 15 parameters, you probably have 2 or 3 where there is a unit-based setting associated with the parameter computation.
Another question for you, R2. Can you merge splats without using a temp class like you did in the example where you used class 21?
Yeah, so you can leave out the non-linked splats. The data set that I showed, which was LiDAR looking only vertically, but images looking both vertically, and a second flight looking at an oblique angle. That was a situation where the oblique images see the building walls in places where the LiDAR has not seen those. So that data set required more the free splats. But if your LiDAR and the images have seen the same surfaces, then it is okay to only bring in splat parameters to LiDAR points and not include any free splats. In some places, the visualization is not going to be as good. So there can be some places where the splat generation creates more splats than you have LiDAR points. So the more the surfaces seen are 1-to-1, and the more the density is 1-to-1, then the more it's a case where we don't need the free splats brought in.
We got another Gaussian splat question. Can the LiDAR files that are merged with the Gaussian splat attributes be saved as an LAZ format?
Yes.
Excellent. We've got some machine learning questions, a lot of machine learning questions. Is machine learning possible in the UAV version of Terrascan?
Yes.
And then here's another question about the machine learning. Can I train the algorithm once and use it on many other projects, or do I have to start over for each project?
You can use the train model if your data set is similar to the data set used to build the model. So if you have used the same LiDAR, then and the same flying altitude, then you are probably going to be able to use the same model. One thing you also have to take into account that it has to be the same classes that you want to classify into. So if the customer requirement is different, then you have to build new training data. But if the customer is happy with the same classification that you have delivered before and build a model, then you are able to use that trained model.
So customers who are doing similar types of flights for the same types of products can typically use those same models or build upon those models as they continue.
Yes.
Excellent.
And it is of course possible that when you have a new data set that you classify a few blocks carefully, and then you build a better model where you use data from the previous data set and from the new data set, and then you get probably a better model. So always the more training data we feed, the better the model becomes at handling different environments.
Here's a good question, kind of touching on the diversity of the data sets within the different groups. What will be the best model testing parameters for both flat and slanted roofs or buildings, or should we use separate testing parameters for the different types of roofs?
Well, that one is a hard question to answer. So you may take the strategy that you train a model to classify directly into very detailed classes, such as you might have a flat roof and a slanting roof as separate classes. Or you can take the strategy that you first classify the data into not so many classes, more generic classes that you only use first in the first phase. You only classify into building roof. And you run a later round in which you separate from building roof to subclasses such as flat roof or slanting roof. And I don't know which strategy is better. So when you start to have a lot of classes to classify into, I'm not sure if the best strategy is to try to classify everything in one round, or if it's a better strategy to classify as 2 rounds. The 2 rounds strategy has the advantage that if you have to do any checking or manual editing after the first round, your manual editing is simpler when all you have to do is decide if something is a roof. So if you have 50 different classes that you have to classify into, and you have to do manual editing, then it is a difficult task for an operator to catch everything, which is a flaw when there is 50 different classes to classify into. So the simplifying one round, doing multiple classification rounds has some advantages, and I'm not at all sure which is the best strategy to follow.
All right, we're running. Sorry, go ahead.
The key thing in the machine learning, based on what is available in the more traditional classification tools in the software, the key thing in the machine learning is really that you can create the list of classes to classify into, and that the parameters have a lot of abilities, and there's going to be more and more parameters appearing in the software. So it gives you a better capability to classify automatically into whatever set of classes that you require.
We have a lot of questions and interest on the machine learning especially, but we're running a little late. I think we have time for one more, which kind of dovetails into what you just said, which is, can I include wire conductors and insulator classes in machine learning in my trained model, or do I have to use the detect wire tool instead?
For the wires, I do recommend that the wires we find with a separate tool, and we leave it outside the machine learning. And the insulator also we need to do, at the moment, we need to do manual work to get that. So the classification is based on, the machine learning classification is based on grouping. So only those objects that the grouping is capable of separating as their own groups, we can classify using machine learning. The insulators, we would be close to grouping if we can first do the wires and we can do the towers themselves and classify those out. But I don't have a classification that would classify towers and not include insulators. So at the moment, the machine learning and the grouping together are not capable for insulators.
Yeah, I think on the classification, the insulators are always the really challenging thing to get, and being able to do that with the machine learning approach would be really fantastic. Well, we are unfortunately out of time. We went over a little bit, but I'm going to pitch it over to Carolyn to talk a little bit about upcoming user conference in North America for Terrasolid, where we'll have the opportunity to go in much more depth over 3 days over many of the Terrasolid workflows, including a lot of the different new features that we just did not have time to cover today.
Excellent. So mark your calendars. The Terrasolid North American User Conference will be taking place October 2026 in Memphis, Tennessee. Registration opens February 2026, and we encourage you to register as early as possible because space is limited. Follow us, Vertical Aspect, on LinkedIn. Stay updated on conference announcements. This is an event that you won't want to miss. Whether you're a longtime Terrasolid user or just getting started with the platform, Terrasolid's user conferences offer invaluable learning and networking opportunities. So once again, thank you all for joining us today. As a reminder, the recording of today's webinar will be sent to you via email. If you have any follow-up questions, please do not hesitate to reach out to support@verticalaspect.com. Follow us on LinkedIn. Keep an eye out for future webinar announcements and details about the 2026 user conference. Huge thank you to Artu and Christian for sharing your expertise, and thank you to all of our attendees. Have a wonderful rest of your day, and we look forward to seeing you at the conferences.
Thank you.
Thanks,
Thank you,
everybody.
everyone.